It's not the one.
Okay, so here's what we're doing. Ready? Everyone say hi, Lindsay, and hi, Spencer.
Hi, Lindsay. Hi, Spencer.
Okay. So this is more.
Oh yeah, 7, Justin.
Hi, everybody that's gone.
Okay, listen. So we're gonna move forward. Okay, come on. Okay, listen. So this is more for Heather and Sasha. There's something that is, in all honesty, if we do not derive this formula for you, you might as well just cease living. I mean, it's just one of the most amazing things ever, and it's so amazing that if you look at your teacher page, I put on, we have to derive this equation right here. Let me tell you this. And I'm not being literal. I don't think I ever want you to cease living. But life will cease to have meaning unless you really understand where this equation comes from. And it is one of the most amazing equations. It is actually engraved on Euler's tombstone because he did derive it. After all, it's called Euler's formula. But this says e to the power of I. Can we do the lights off? Can we do the lights, please? E to the I pi equals -1. That is Euler's formula, and it's Euler's formula applied with an identity. And one of the things I have to admit, one of the most beautiful statements to ever be derived, probably my favorite mathematical entity in the world, is this right here. But to get to here, it requires deriving what's called Euler's formula. And do you see on your, I said how far, now if you do this, you will get an A in the course.
There was a former Shady Side math teacher who had that tattooed on his arm.
I think he had pi tattooed on his arm.
Both.
Oh yeah, okay. But now I'm kidding. So Spencer or Lindsay, if you're listening to this with your parents in the room, please make sure that I'm in no way making you tattoo or burn yourself or brand yourself with Euler's formula.
Is this a tattoo? It looks like it's brand.
That looks kind of like bird.
Yeah.
Possibly. Yes, those of you going to college next year, if the fraternity's hazing policy includes this, by all means join. What's wrong? Okay. Sasha and Heather and Spencer and Lindsay. So for us to get there, I have to give you the background on what are called Taylor series, which is actually, to be fair, a huge unit. And one thing I struggled with was, how do I get to here without really doing series, giving it its full due? Because if you remember from BC last year, that was not like a 2-day unit, right? That was it was a lot, and people often hate it the most. But I can give you the bare bones, which is this. What you're looking at here, Heather and Sasha and Spencer and Lindsay, is just your y equals sine x graph. One of the problems that you have, Severn had BC last year. I'm talking to the AZ people, okay? One of the problems that you encounter when you first see the y equals sine x function is most people will say the sine x function has all the graphical properties of a polynomial function, which is it's smooth, continuous for all real numbers. There are no points of non-differentiability. And so the natural question was, there has to be a polynomial function I could use to describe this. There has to be, because it has all those graphical properties. And without getting into too much of the detail, if you look here, look at this function. I'm going to go ahead and click it on in a minute, right? There is a cubic function that seems to really well approximate y equals sine x in this region right here, okay? And this is cubic because power of 3, power of 1 is a degree 3 polynomial, okay? And then what happens is, if you then kind of turn that off, and let's say, well, let's just add another term. Let's look at a 5th degree polynomial. And what you see happening is it's a very interesting situation, whereas now I go to a higher degree polynomial, and it tends to morph itself even more to the graph of y equals sine x. And then the question is, what happens if I keep with this pattern, the pattern being adding successive terms, alternating the sign, having only odd degree terms, dividing by the same factorial as the degree of the term. And look at this. This is a 7th degree polynomial. Do you see how this polynomial function is kind of bending itself to the sine function over even a wider interval, right? Okay? And then I just went and did one more, but we can sit here, for infinity and put in all the terms of this, and here is a degree 9 polynomial, right? So a big question last year in calculus was, what kinds of functions, because not all of them do, what kinds of functions lend themselves to the most user-friendly function. Polynomials are the most user-friendly function. They are defined for all real numbers, they are smooth, and they are differentiable for all real numbers. We love work. There's nothing else to think about. They're very predictable. We know their end behaviors. So the big question was, what kinds of functions can we essentially model with polynomials? That's how your calculator, by the way, when you go and put sine 240, what it's doing is it's kind of using a program. If you look at this, it's a very, very programmable entity, right? When you plug in sine 225, your calculator doesn't have all the sine values in its little chip. If it did, it'd be this huge, monstrous thing. What your calculator does is it uses a polynomial approximation to get a sine value accurate to, I think it's 10 digits of accuracy on your calculator, right? So that's a great question. So clearly you see here that if I wanted to use this polynomial to approximate sine of 4, do you literally see the error right there? I'm off, correct? There's two ways to diminish that error. One is to just add more terms. The second one is to take, this is like the center of the approximation. This is where this polynomial has 0 error with the function sine x. The second way is to say, well, is there a way to, instead of having my center be at 0, can I have my center be at 4 or 3, okay? So therefore, it kind of will radiate out from a different center, so to speak. So that is, and that kind of is the unit of series in a nutshell. Given a curve to approximate that is not a polynomial, first question number 1, can I approximate with a polynomial? Where should the center point be? Here at 0. And then also, how many terms should I go out? That's the third question. And then the biggest question is, if conceivably I could go out to the infinitieth degree, would that polynomial actually equal y equals sine x? Would there be no difference whatsoever? Do you understand? Okay. So I'm kind of giving you that in what was that, 3 minutes? Dr. Robo, you're coming to class. Whee!
A little bit.
Sorry, I'm driving for this one. I'm so excited. Yay! Is statistics? Okay. Yeah. Yes. Okay. Everyone okay? Okay.
None of these children are in there, so give my children a hard time.
Okay. Who just left?
Bobby.
We can wait.
Okay. Well, he knows the story, right? He knows. Okay. It turns out, do you want to know what the answer to this question is? It turns out that in the case of sine x, this polynomial, if I add a dot, dot, dot to it, and when you add a dot, 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 what you're saying to the reader is, this polynomial taken out to the infinitieth degree. It turns out for this polynomial with a dot, 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 not only does it approximate sine x, it equals sine x. I'm going to let it sink in.
But how do you know that?
Yes, you prove the interval of convergence.
Oh, yeah.
Okay? Remember all that? So, that's that in a nutshell. There's a couple things, and that is, all you have to know is how the story ended. We don't need to go through all the math for us to see something that is quite possibly the most amazing thing in the world, which is this. I wonder, should I just do the notes on here so Spencer and Lindsay can get the full experience?
Sure.
I think we should. I'm going to go up and get my pen so I can write there, and then why don't you just talk to them so they don't have silence while I'm gone, okay? Okay, good.
Hi, guys.
Hi.
Hi.
Spencer, you missed econ today, but really tough quiz.
Let's see, jump high. Well, I guess when you see this, you already know how.
Wait, today?
Nick, running fast.
Nick, physics test got changed tomorrow, buddy.
What?
No.
Don't worry, Nick. You'll do better than me. It'd be really funny if you can't even hear us and this is what's wrong about audio quality.
True.
That'd be pretty dumb.
Wait, where's Spencer right now?
Spencer,
where are you?
Spencer, where are you?
Why did you go on that field trip?
Yeah,
Yeah,
sports
it's-
is
it's-
where
You
It's
was
not-
this
it's
close
not-
to not being forgotten. Like,
Is he in that class? Maybe he is in it. Oh yeah, because he drops
That's a really poorly drawn sine curve on the board.
Swear. Triggered.
Oh wait, never mind. I thought that was supposed to be like sine and cosine.
I also have muffins.
For us.
Since this is a day that I just stole them from that. No, but they're relative. There's only 5 left, which means you can
Fight.
split one.
What did
Okay.
look like?
Spencer, I'll eat your muffin.
Spencer, you want to
So,
split?
Okay,
Okay.
so where this is leading us, and I promise you, this will all come back to Diffie cues. Okay, where this is leading us is here. Okay, and I think what you're going to find too is. And Lindsay did find me and say, like, I'm not going to make it to class today. So, oh no. Okay. Are you ready? So, here we go. So it turns out, here's the situation. It turns out, you heard that story. It turns out this is the case. Sine x, cosine x, and e to the x are 2 functions.
Three.
That would be 3. 3, what?
You don't have to whisper.
Well, it's a stylus.
But oh my god, I always thought you wrote with your mouse, like Sal Khan.
I don't understand how he does.
Like Khan Academy. Like
How do you
Khan
write
Academy.
with your mouth?
You know, you always hear him.
He uses.
Wait, that's his mouse? I think so.
No, it's a stylus. It's a
No,
stylus.
Sure.
Sorry.
I can't imagine someone's that good with their mouse. That'd be so hard.
Yeah.
Okay. It turns out. So now you have the story. It turns out that sine x, cos x, and e to the x are 3 functions. None of them are polynomial. These 3 functions actually equal, not approximate. They are equal to these polynomial functions. And let me put them up here for you.
Is that the same with like x and 1 over x?
Yes, indeed. Yes. And so that's like ln x I think is only over it's only from 0 to infinity,
Oh yeah.
right? Which makes sense, right?
Yeah.
Wasn't it
Was that my fault?
Wasn't it 1 over? It wasn't 1 over x.
10 is. I had to click it so hard.
There were 5 functions that we
It
did
hurt
last.
my
Yes.
What are the other 2?
Ln x over x and then 1 over 1 plus x. Yeah. Okay.
So those are all that. It's not the right.
Okay, ladies and gentlemen. I will say this. There is this part of this lesson you don't have to write down. I will never ask you to derive Euler's, but if you want to ensure that your children and grandchildren are raised properly, you may want to have this story. I mean, that's your call. But I mean, if you want to be able to communicate valuable information to future generations of Zunders and Arafievs and I almost said Bayless, Robbie Bayless, a student of mine ages ago, Svedas, you may want to tell them the story. But I know it's on email because Robbie Bayless was my student years and years ago, and he's now 33. But
It's like Robbie looks like he's 33.
yeah, that was before. Yes. Yeah.
You have to do the surprise, either sine x or cosine x.
Right. Okay, so here is the thing. So this is the derivation. I will tell you what you do want to take down at the end, okay? Now, listen. Here is what is amazing. So these 3 functions, notice the equals. These actually equal these polynomials. And this is the result of probably easily a 4 to 6 week unit of study. I mean, the question becomes, is it possible for all kinds of functions to be approximated by polynomials? What's the big whoopee? Why do we care? Are there some functions whose polynomial equals the function to be approximated only for certain x values and not over its entire domain? I mean, those are all the kind of tertiary questions, right? But the point you have to know here is these 3 actually equal these. They're called polynomial series. Okay, a series is just a sum of terms. We've called these polynomial series. Your comrades here know them as Maclaurin or Taylor series, but all you need to know for you all with compromising nothing is that how weird. We have these 3 functions, y equals sine x, cos x, e to the x, that actually equal these polynomials. Okay, now here's where the fun begins. Are you ready? Here we go, all right? Look with me here. Okay, and if you're looking at your book bag, you're gonna get. Wait, how do you know where I'm going to go? I haven't gone anywhere yet. Why are you moaning and groaning already? Like, how do you know where I'm going?
Well,
I said-
I there.
No, I'm not putting pie. No, I'm not. See, don't think.
Replace all the X's with IX.
No. Wait. Just wait. Yes, no, not even spoiling. You're like you're like running over the hill. Okay, ready? If this is e to the x, I'm going to do this. If that is in fact e to the x, and we prove it to be so, we're going to do e to the power of ix. Okay? E to the. Will you relax, Eric? You don't have to get so animated and angry. Okay? 1 plus, just everything's okay. Everyone's okay. All right. 1 plus. Okay. This becomes ix, right? Plus now ix quantity squared. I squared is -1. This then becomes minus. Okay. That then becomes minus x squared over 2 factorial. Okay. Plus ix in for x cubed. I squared is -1. You still have an I remaining. This becomes -I x cubed over 3 factorial. Okay, everyone okay? I know, Connor. I know. It's okay. Right? Now, ix in for x here, I to the 4th is +1. So this becomes plus x to the 4th over 4 factorial. Okay? What's the matter, Oliver? Tell me.
So it's alternating in groups of 2.
Well, we can keep going. Let's keep going, okay? Ix in for x to the 5th. I to the 5th is going to just equal I. Why? Because I to the 4th is 1. I to the 4th times I is just I. So this next term becomes plus I times x to the 5th over 5 factorial. All right? One more time. The next term here would be x to the 6th over 6 factorial. Ix in for x is going to be I to the 6th. I to the 6th means I to the squared 3 times, which is -1 times -1 times -1. We get negative x to the 6th over 6 factorial. Now, once again, let's just make sure we're clear. I want you to experience this. This should be like a full body experience, like from the fingertips to the mind, toes, all of it, all right? This is indisputable. That has been proven. There's no dispute to e equaling this. E to the ix is just merely doing a function operations. If e to the x equals something, we're saying that if f of x equals something, f of ix equals, replace all the x by ix's. Now, observe. Look at these terms. Are you ready? Wait, Oliver, wait. Listen, look at. Okay, wait. We're not. You know what? You are like Christmas morning, just ruining the surprise for all the younger children. Okay. 1 minus x squared over 2 factorial plus x to the 4th over 4 minus x. That's just equal to what? That's just cos x, right? So e to the ix will equal cosine of x. Oh my! What else is left? This, and this is just equal to plus I sine x. Okay? Now, let me just make sure I think this is where you want to write this down. E to the ix, we have just shown that e to the ix equals the cosine of x plus I sine x, okay? This is called Euler's formula. It is amazing. Those of you who've seen it before, I'm sure you've never appreciated where it came from. This is called Euler's formula, okay? This is the most important day of your lives. This is Euler's formula. Why is this profound? Max?
You related imaginary numbers to real numbers?
Yes! And? Any other ideas of why this is profound? All right, everyone. Dare I think your generation is called the cynical generation. Nothing can make you excited, but prove me wrong. Euler's formula is here. e to the ix equals cos x plus I sine x. This means e to the I times pi should equal cosine of pi plus I sine pi.
Sine of pi is 0.
So e to the power of I times pi equals -1? That defies all reason and logic. How could e raised to an imaginary power give you what?
But I'm confused. You get
A real number.
No.
What? Tell me.
You still have
You
the eye.
still have the eye, technically.
No, you do not.
Sine 0 times I is
Oh
0.
my god.
Oh my gosh, is right.
Well,
I'm
Okay.
essentially, you just like found a way to raise a real number to a power and get something that's negative. You
No,
just, like,
raise
screw up.
something to an imaginary power.
Or no, I'm saying, like, if you said, "Oh, raise something to a power and get a negative," you're like, you can't do that.
Yes, you
But,
can.
Like, but
Also-
apparently you can.
Wait a minute. Wait a
Could
minute.
anyone just make up a number and then it would work?
Okay, wait, hold on a second. Max just said you can't just raise a number to a power and get a negative number. I'm going to refute that.
But not without that, right?
He meant positive.
In a positive power, that's true.
Or no, when
No,
you're just
positive
thinking,
number.
whenever you're just
Oh.
thinking about exponents like a normal person, everything is like 0
Raise
and
two
infinity.
to
Oh,
something.
I see.
Yeah.
We are no longer normal. This is amazing. And frankly, how about this one? How about this one? How about this one? Ready?
It's definitely a whole.
There's a hole. There is no hole.
Wait, also though, couldn't anyone just make up a number and then
Where are you making up the number? For what? X?
I?
I is not. I is a number. I is root negative
I
2.
have the square root of negative
I know,
one.
Yeah.
who decided that?
Wait, you
What?
can't.
I mean, that was like that. That was just. I mean, that does not make that. Oh, you're
Like,
saying
couldn't
like,
anyone just make up an imaginary number and then use
Okay.
that
like couldn't anyone just call I something else?
or just make up
I mean, I could be
something
like,
else that's the square root of -2 and say it's like,
Oh, sure. Yeah.
and then
Yeah.
use that.
What about Jane?
What's that? Yes, but the thing is that would still work. You said someone said let's just call m the root of -2. The response to that would be if m is root -2, like -2, I can break that down further because -2 root, right? So
But
really,
also, sorry, the fact is that like that wasn't made for this purpose, but it still works,
correct,
which is crazy.
Yeah, like they
What
found
purpose was it made for? Why?
Oh well, so now Oliver's saying, how does this have relevance to us in differential equations? What a fantastic question.
Well, I was talking about I specifically.
Oh,
Why is that like
the imaginary point.
what?
Because you're like, oh, well, geez, you can't, taking square roots of negatives doesn't make sense with real numbers, so we need a new kind of number to represent it.
But why just with -1 and not anything else?
what do you
Because
mean? As opposed to what all like root of -5. Yeah, because so basically the point of your question is why start the origin of negatives?
Oh, then you can just multiply that.
Exactly.
Okay.
Exactly. Right? Okay. This should be kind of mind blowing. Similarly, okay, hello. Okay, how about this one? What would this equal then? What is e to the 2 pi I equal to?
Negative
No, it should be
-1.
1. Would it be? Would it
One or
be
the other.
One.
E to the 2.
One.
It equals 1.
It's -1 squared.
Oh, yeah, so it actually works both ways. You took this and you squared it. -1 squared is positive 1, but you could have also just plugged in 2 pi for x, and you would still get positive 1. Okay? Now, let's go back to the person, okay? And here she is. E to the I pi plus 1 equals 0, because we know e to the I pi equals -1. This is generally how it's seen in, like, out there in the world. You want to know why this is so fantastic? One equation incorporates irrational number, imaginary number, real number, and 0. Like, that's pretty profound. To have every class of number, generally speaking,
Entrance.
and transcendental.
What
Exactly.
is E under the category of?
Transcendental.
Transcendental function. E is a number, it's just irrational number, right? E to the x is a transcendental function.
I was
Uh,
thinking pi of the same kind.
Correct. I think transcendental numbers is kind of out of fashion. Usually the transcendental.
I just thought it was a special kind of irrational number that can't be expressed using like square roots or fractions.
That's all irrational numbers.
What's the half?
No, root 2. Root 2 isn't transcendental, but it's irrational.
Oh, because you're taking. Oh, so because it can't. One more time. Oh, because it can't be expressed as the square root of a number.
Or any
Oh.
root
Oh, I see.
Right,
So the
yeah.
class of irrationals that's not a
that
root
can't be
Oh.
expressed
is
as
transcendental.
Is transcendental.
I don't remember it. That's a lexicon.
Well, the
Can't
class
be
that's
classified as a
something.
root of a whole number.
Correct. I don't remember the lexicography of that. I'll look it up.
I thought that was.
But I mean, this equation is amazing. The most powerful numbers. The only thing missing in here. Who is missing in this picture? Infinity. You're gonna get really impressive, right? Like if that's.
What if-
But
Oh wait, you can't.
but
put
this
an
is the closest
infinity
we've got.
to a cosine or sine because it doesn't like have approach any.
right. Right. That's pretty fantastic. Do you agree?
Did he put that all
Wait,
with
also,
zero?
infinity times 0 is
Okay. Infinity times 0 equals 0.
Oh,
Something approaching infinity times
I see.
something approaching 0 is indeterminate.
okay.
Okay. Very
I'm
different.
curious.
You could just multiply 0 by infinity.
And it equals E if they're like.
All right. Which then leads us to Diffie Qs. Very good. Let's go back here. Okay. And I'm just staying on here because we're recording class for our missing comrades. Okay. Where we left off, right before the test was looking at, we looked at second order differential equations with constant coefficients, set equal to 0. This is our recall, okay? Recall. And Jeannie, I have an answer for you. We left off with talking about second order homogeneous differential equations with constant coefficients. Remember I said we know that the solutions will be of the form y equals e to, I think I called it rx, or m times e to the rx, right? Or I think I said y equals m times e to the rx, remember? And you said, why do we know that? And I said, there has to be a reason beyond just recognizing that e to the x, e to some power of x, is unique in that its successive derivatives will always contain e to the rx or m to the rx, right? And so when you look at an equation like this, there has to be some function whose successive derivatives can somehow cancel each other out. And you said, like, how do we know that e to the rx is always the solution form? And I said, and I think Eric said, well, think about it, e to the x, e to the power of something x will always have itself in its derivatives. And I said, Fred, that's just a pattern. There has to be more of the reason than that. It turns out there is no more to that reason. It's simply because we know that this is going to be a solution of this because of the nature of e to the x and its derivatives. That's it.
Wait, I was just going to say that. Should there be some special, because sine and cosine are like cyclically related?
Yes, and that is the case in non-homogeneous concepts I'm going to next, and you'll see why in a second. Well, let's just make sure we pick up where we left off. This was the last new topic that was not included on your last test. Let's just do it out so we recall completely, okay? So we were given a second order homogeneous Diffie Q with constant coefficients. You knew that this, what did we do? You tell me, what did we do? Yes, Oliver.
We did the derivative and second derivative.
Yes, we did. We said this equals, y prime equals mre to the rx, and y double equals mr squared e to the rx. Comprende? Yes? We jammed this back in here, and we saw that mr squared e to the rx minus 3 mr e to the rx minus 10 e to the rx equals 0. What will always be the case?
Wait, 10m.
Did I lose an M?
Yeah. 10m.
Whoops, I lost an M here, everyone. I lost an M. Okay. What will always be the case? What can factor out? Right. And you're always left with r squared minus 3r minus 10r. Oh,
Whoa.
10. Sorry. equals 0, right? So with these, you can automatically skip to here. This, by the way, when we talk about solving a second order homogeneous Diffie with constant coefficients, this simplified equation is called the characteristic equation, okay? It's the one that we're ultimately going to use. It's the characteristic equation. And then we went, and tell me if I'm correct or not. I'm setting this factor now equal to 0, correct?
Yeah.
And it is factorable. Will it always be? Oh my word, that's a really good question. Okay, r equals 5, r equals -2. So we have two solutions. One of them is y1 equals me to the 5x, y2 equals me to the -2x. We know, yes?
Sorry, I don't think what we did before, we didn't have that constant sig at the beginning.
Yeah, we did. This one?
I think
We did.
we just said e to the rx. We didn't put
And
that.
then at the end we had C1 and C2.
That sounds right. We like to put it on at the end.
Wait,
We said,
I
and
agree
don't
with-
forget.
I
like,
got it.
Didn't we talk about how to be any linear combination?
Yeah, but that, yep, that was, this. So we left off here on one day. And then the next day I said, right? Wait, what did you say?
Wait,
well, I was saying we started with like just y equals e to the rx. We didn't start with
Oh, we didn't have a constant. Okay, are you okay with just adding it here? Like it could have been a constant, right? Okay, now what we said was, what we learned was, we talked about functions that are linearly independent. Okay, what does that mean? Shall we look it up or shall I tell you? Maybe I'll tell you. These two functions are linearly independent because y1 does not just equal a constant multiple times y2. Similarly, y2 is not just a constant multiple of y1, okay? So these two solutions are what are called linearly independent because y1 does not equal some constant k times m, or times, I'll just call it y2, times y2. Are you all okay with me?
Wait, couldn't that constant be like e to the some weird power?
yeah, no, I was about to say that. But
Try it.
When you multiply the constants, you add them.
Correct. That's right, you add. There's no way, like if you multiply by e to the 7th, for example,
Does it equal e to the 5x plus 7 all in the thing?
Yes.
yes,
Oh,
yes,
yeah, that's not possible.
right? It is not possible. What is the case if these two are linearly independent? Therefore, we then said all the solutions, every solution, all the solutions, the original Diffie is a linear combination of the two solutions. Comprende? Okay, yes. Jeannie?
I remember I asked this last time.
Yeah.
But I don't remember the answer. So for a first order, right? These are second order.
Yeah.
Yeah. For a first order linear Diffie
Yeah.
the solution we just have one solution.
Correct,
Right? So
correct.
then it's like it's like sort of linearly independent, but like not really, because
It is. It means that, so if you only have one thing, that one thing is always linearly independent because there's nothing else to compare it to. All the linear combinations of one thing just means any constant multiple of it.
right. Okay.
Okay? The point is, when you have linearly independent solutions, you can then say, therefore, the general solution to the original Diffie, what did we say, Heather? We said is y equals
E to the 5x plus
C1.
any multiple of the first one, me to the 5x, plus any multiple of me to the -2x. And this is where I think Oliver was saying we didn't have an m here, which is fine because do you see how c1 times m is just in and of itself a constant, c1, okay? This is called right here, this is called a linear combination of the independent solutions. This is where we left off. Are we all together?
Wait, we called it like bounded value.
No, we did not. That was something different. That was something completely different. That was something completely different. Heather, what day did we talk about this? Can you help me?
We talked about it on the
Wait, go back.
the 18th.
Yes. Okay. So this here, this is where we left off. Everyone good?
No.
No. Okay.
It's not here. It's standing written down.
Could you go up just a little bit?
Sure. And the reason why I actually hate not moving around because I feel like I'm not moving around, which is true. But the other thing is, this is such an important day. I don't want half the class to not get it. I also realized something else. I was talking kind of loud, which means on their end, it's going to sound like Miss Yam is like screaming over the volume. I know, but then they can't hear what you say. You know what I mean?
We're less. Because you're the one.
Or they can put us on the Bose sound system and have us like blaring at decibels on their car stereo.
I mean, it would be less than whatever song it is.
This is true. This is true. Okay, everyone good? Okay, fantastic. There's a word that I want to say, and I want to say it so badly, but I need all of us here for me to say the word because it is the most funniest word ever in the mathematical lexicon. I'm not going to say it. I'm going to wait till they're all here. So I just have now changed gears. No, but I need everyone to say it with me, and then all of you to look around and look at each other's facial expressions.
Demand that they.
No, I can't.
Invite their family in the room and have them.
Nope, can't do it.
I mean, when you said lemming one class, I don't know.
Really?
Using that word.
That's so funny. Really?
In bulbous.
Well, that's because we don't have like 3D graphs to look at. Yeah, I know.
True, yeah.
I love when you just said undulating.
Undulating, I know. Or like Eric's head as a vector field, right?
That is fun.
Okay. Here is the natural next question that we are going to tie into Euler's. Are you ready?
Yeah.
What you notice here, this is no different. Second order, constant coefficients, homogeneous. However, it is not only is it not factorable, it yields imaginary roots. Okay? And this, are you ready? So we're gonna when we know if we do a ... Oh, Oliver, make sure you just left here, right? See how you were saying I didn't have an m here? I always had just C1 e to the 5x.
So it doesn't matter.
But C1 times m is just another constant, okay? All right. We know that the characteristic equation, this diffie-q is eventually going to yield the characteristic equation. I'll just drop the e. How about that? E to the rx, right? And we're going to get r squared plus 2r plus 3. We know that's going to be the case. Okay, we know that to be true. When we go ahead and solve this, the characteristic equation, we're going to get imaginary roots. Now, I'm going to actually complete the square here. That's always easiest when the lead coefficient is 1 and the b term is even. This becomes plus 1, yeah? We all good? We then get r plus 1 squared equals negative 2. R plus 1 equals plus or minus root of negative 2. Let me see. Oh my gosh, it's...
Like, I'm confused, like, do you multiply?
Mr. Tony taught it, but I just didn't pay attention.
How do you, like, make a perfect square?
Trinomial?
You just
Great, ready?
Like, you multiply the a, like, b times 2 to divide by 2.
Is your question, how do I get this plus 1?
yeah.
Yeah, how many?
Take b,
Yes.
have it,
Have it.
square it.
I need that.
Okay, b over 2 squared. No, divide by 2, then square it.
Anyway, that's what you're saying.
Yeah, okay, divide by 2, then square. Everyone with me so far? Okay. When you have a second order, this is a mouthful, second order, constant coefficient, homogeneous diffie-q, when we have imaginary values for r, this is a very special case. This is called the lambda mu case. When we have imaginary or complex roots, in general, what happens? The question here is, what is the deal when we get r equaling a complex number of the form lambda plus or minus mu I? Okay? And here, clearly, lambda is -1, mu is radical 2. What happens? Like, because really, we can just go and do this, right? We know. Okay, we know that we could just be kind of the human beings that we are and say that one solution is y1 equals e to the -1 plus I root 2 x. You follow? The other solution is y2 equals e to the -1 minus I root 2 x. And then we would say, to finish the problem, because we were after all asked to solve the diffie-q, we would then say that our general solution, that which includes all the solutions, would be y equals, here it comes, factor of the first, e to the -1 plus I root 2x, plus c2 e to the -1 minus I root 2x, and call it a day. This is not wrong. This is the general solution. All right? But if we use Euler's formula and a little bit of algebra and hang in there for the whole ride, there's a really satisfying conclusion. Would you like to go on that ride with me?
Of course. We have time this period.
Is it? Do we have time this period?
How long would it take?
Yeah,
We have like.
let's go on a ride.
Yeah, we have 6 minutes. Is it will take?
We only have 6 minutes?
Yeah, it's 2 or 4.
Yeah.
Wait a minute. Don't we have until 2:15?
No, we lost time.
That's
Oh.
on Tuesday.
Oh.
Let's go on a ride.
It's
It's
1
really
Tuesday.
fast ride.
Shift which way?
I
Boop.
just need to see, yeah.
Oh.
What's the deal with-
What is the deal? Like, what is so special about having, look, imaginary, like when the roots of the characteristic equation are imaginary? And one more time, be careful. Listen to my language. The roots of the characteristic equation corresponds to the coefficients of the x of the power of base e. Okay? So, and also, just so we don't leave sounding silly or, embarrassing ourselves at Coffee Tree, this here is lambda, okay? Please don't call it like TP or whatever it is you want to call it, okay? Lambda, this here is mu. That's mu. Euler is EULER, Euler.
I had it right.
Why is this name pronounced Euler and not Euler?
Everyone asks me that, and I don't know.
I think.
I don't think it would be Euler.
He's oil. We
I don't
figured
think
this
that
out
was it.
in math class last year. We actually looked it up.
Is it, well, what's the reason?
I forget.
Why it's called Euler, not Euler? Yeah, I don't know.
I would guess.
I mean, probably the same reason why my name is Yam and not Yam. I mean, just, I don't know. Just it is.
Oh, yum yum.
6 minutes is not enough time for me to start this ride with you. Yeah, we need a good 15 to go through this. And I can't start it and we can't cut it short. So you know what? I want to make sure you know this is a fine way to leave the solution, but put a big fat but. We could express this a different way, and that different way we will continue. Do we have class tomorrow?
We do indeed.
Okay. Oh, fantastic. Now, here's where we're going. We're going to finish this, then we're going to talk about non-homogeneous second-order diffie-qs with constant coefficients,
Where cosine and sine get to be special.
where cosine and sine get to be involved in the picture, okay? The other thing that happens, then we go to what's called, remember you asked about the funky L? You and Eric asked about that, the funky L in the textbook?
Oh yeah.
So your text uses a cursive italicized L. I've always just seen that as a lowercase L. It's called a Laplace transformation. We'll do that. The Laplace transformation. So, funny story. Laplace transformation, that was the brainchild of a mathematician named,
Laplace.
I think, René Laplace.
Of course.
René Laplace was married, had an affair with his cleaning lady.
Oh.
The affair resulted in a child who was the bastard child. And the lineage of that Laplace became Miss Kristen Laplace, the former athletic director at Ellis.
God.
And so, I said, Tristan, she said, are you related to Renee Laplace? And she said, who told you? I said, no one, I'm just asking. And she said, well, it's a story that you really can't share. And I said, well, tell me anyway. That's the story. So she said, well,
So
yes.
you are sharing.
In that I am like the result of this bastard union between Renee Laplace and his extramarital affair.
That's hilarious.
She was the descendant of that lineage.
That's hilarious.
Missy, how do you get all these cool stories?
Yeah, why?
I just am, well, number one, as you know, I'm a little bit socially awkward, so in social situations, I will ask about things that people don't know what to ask about. But it's just, I think it's fast. I think, here's the thing, to make it a learning moment, I think the thing is that there's so much around you that I think sometimes you don't, it's so easy to overlook what's around you, right? Like the miracle of the everyday. And here's a woman, and this is someone, she was getting her master's degree in nutrition, something that's another, right? And so she needed some help. And she said all the math was like lost on me. So she says she got the cleaning lady side of the math gene. Like Renee Laplace passed none of that on in that zygote formation, right? And so she says, yes, it's something that we're not proud of, and we really can't speak of it, and it's not a source of pride on their, it's because she's the result of she's a descendant of the maid's son, right? Like she's that.
I feel like that's gotta be enough centuries past that you wouldn't care anymore.
Well,
How
I
old?
don't
But
know.
it's still,
I don't know. It's like 17,
That's the-
plus and 17. Let's see.
Yeah, why do you care at that?
I mean, if you knew 300 years ago, you are the result.
I would like tell people that. I would think it was funny. Like I would, like Eric would have already known.
Yeah.
Like if that was my family. Like,
Okay, and that's the thing, but maybe it's a sore point in the in the lineage of the Laplace family. I guess Kristen Laplace. But the point is, ladies and gentlemen, that like all of this stuff is around you. Like there's amazing things that just happen all around us. You just have to look and take the time to ask the awkward question. Be awkward, Eric. Be awkward.
Did you
Yeah.
get mine?
I did. I'd be happy to. I am hitting my limit soon, so luckily.
Max,
I have
you're not
16 plus.
They did.
You're not.
You're all done for.